So your exercise was to give me a loop invariant. And here is loop invariant and then run through the proof. Here's the loop invariant I'm going to use for this proof. It's worded not as sort of verbosely. I've tried to make this concise and easy to understand, so we'll just say that at the start of each iteration with indices I and j, because we're going to have two looping indices that we care about, all the items in array from L plus 1 up to and including I minus 1 are less than the pivot, and everything from I up to including j minus 1 are greater than or equal to the pivot. So this is the smaller than partition, this is the greater than partition, and a couple of things that I've done here in my loop invariant is I've got L instead of left index, and I guess that's the only shortcut I've got on this slide, but I did that just to make it easier to have everything fit on the slide, and you'll see what I mean in the next few slides. But what I want to do here is have you pause it again, and now with my loop invariant, if it's much different than yours, try to reason out initialization, termination, initialization, maintenance, and termination. Okay, so this is what I mean by trying to have this fit all on one slide. I've got pivot reduced to pivot value. I'm now calling it pivot up here, L instead of left index, and same thing with the code down here. I'm just trying to take up a little bit less space. One annoying thing that I haven't fixed yet is that I call it pivot here and I still call it pivot value down here. Alright, but this is our conditions at the time of initialization. So for initialization, we just show that the loop invariant is true before the loop starts. So before the loop starts, I is equal to L plus 1, j is equal to L plus 1. So what can you tell me about these two partitions under those circumstances? Well, the first one goes from L plus 1 up to and including I, and we just said I was L plus 1, so that would be L plus 1 minus 1, so L plus 1 up to and including L. And then similarly for the other one. In both cases, there aren't any numbers in those ranges. And it's pretty trivial to say that this non-existing number is less than the pivot, and this non-existing number is greater than the pivot. Greater than or equal to the pivot. So initialization, just like almost always, is sort of trivially true. There are no items that have been considered yet, so we just cannot break our two conditions up here. So for maintenance, we have two cases that we need to check. And the two cases are based off of this this comparison. So whether or not the current element, the current unpartitioned element, is less than or greater than or equal to the pivot element. So again, for maintenance, we're always going to assume that our conditions hold, and since I'm doing bullet points here, it might be a little less formal than I've done in the past, but we'll just say suppose conditions 1 and 2 are met. Now suppose that the current element is less than the pivot. So we're going to assume that this is true, and we're going to execute these two lines of code. So I've not done anything here. I've just, from this slide to this slide, I've just removed some of the text that was up here just for space reasons, and I've moved these two bullet points up. Alright, well let me show you the picture and start showing you the color coordinating here. Our pivot is in orange. Items that are less than the pivot have been colored in green, so that's this less than partition. And again, we're always supposing that conditions 1 and 2 are met. We're assuming that the loop invariant is true upon entering this iteration. That's another way to say that. So we have our less than elements here, we have our greater than elements here. The current element we're looking at here and it is right there, and we're assuming that it's a less than element. That's why I've now colored it green. So what do we need to do? We're going to swap I and j. So here's the element at I, here's the element at j. So those two elements are now swapped. And by condition 2, we know that the element that was at I was greater than the pivot, and by our comparison here, we know that the element that was at j was less than the pivot. So after the swap, we're guaranteed that conditions 1 and 2, we're guaranteed that we've put our elements in this order, where we have our two less than elements here and our two greater than elements here. And then after we increment I and j, so they were here and here, and we're going to increment both of them. After we increment I and j, we satisfy again our conditions 1 and 2. Alright, so that's case 1. That's when the current element belongs in this less than partition. Now let's look at case 2. Case 2 is when this element belongs in the greater than partition. So we're going to, again, suppose that conditions 1 and 2 are met. And we're going to assume that the current element is greater than or equal to the pivot, which means this is false, which means we don't do anything inside the loop. We don't do anything inside the if statement, but then we do increment j as part of the for loop. That's the last thing we do as part of the for loop. So we don't change I, which means condition 1 holds, and we increment j, so now that condition 2 holds. So that's our maintenance condition for both possibilities of this if statement. Alright, for termination, we have that j is equal to r. So when j is equal to r, this loop will break. When j is equal to r, all elements in our subarray have been considered. We haven't manipulated anything inside the smaller than array, and in our greater than array, we know that everything from I up to and including j minus 1 are in the greater than partition. So now we can say that, okay, everything has been correctly partitioned. And while not necessarily part of the loop itself, we should end by saying what do we do right after the loop. We're going to swap the value that was here, so 1 to the left of I, with the pivot, and that's going to give us our correctly partitioned subarray with the pivot in its correct final spot.